So going back to that problem where 18% of college students are drinking energy drinks on a regular basis, don't do it. It is not healthy. But here is a random sample of 5 college students. We got Beaker, Mickey Mouse, I don't know what that is, and then Potato Head here, and then this guy, Mr. White. He's Breaking Bad. He is Breaking Bad. But anyhow, so we got these guys right here. So here's the deal. We want to find the probability of getting exactly 2 out of the 5 people energy drinkers. And so we could have a success and a failure, failure, failure. Now, what if we did this? What if we put Potato Head over here and switched it with, I don't know what that is, but if we did that, we'd have the success here and the failure here. Now, it might seem like that's a different situation, but it's not. All we did was move Potato Head this way, and I don't know what this is, to the left. So it is still the same 2 people out of 5 that are the energy drinkers, and that's why order's not important. The order we put them in is not important at all. All we're saying is, okay, if this is your success and then your failure, 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 it means these 2 right here are the ones that are the energy drinkers. If instead we do see this and this, now it's Mr. White, and I don't know who that is, that are going to be the 2 successes, and the other ones are going to be the failures. But do we also agree that we're going to have the same probability combination? We're going to have 2 successes times 3 failures. So no matter how we decide which 2 are going to be the successes, we are going to end up with 0.82 to the third times 0.18. I'm going to move this over so we can actually see the whole thing here in a second. We're going to get 0.82 to the third, and we're going to get 0.18 squared. But then here's the thing now. We got to figure out, so how many ways can you pick 2 of these 5 to be the successes? You could look at a tree diagram, but what we'd rather do is just understand that whole notion of combinations. So we're going to say, hey, if there's 5 people to choose from, then this is the number of ways that we can get 2 people out of 5 that are the successes. So we multiply each way, each probability for each single combination times the number of combinations, and that will give us our answer. And so we're saying, hey, what's the probability that x equals 2 successes? That's your probability right there. Now, something else that's beneficial. If we say, okay, random variable x is distributed binomially with n and p, so in our case, n is 5 and p, the success rate, is 0.18, then we can say, oh, okay, well, this is n, this is p, and in our case, we want to find the probability that x equals 2 successes. So this is k. And once you have the n, the p, and you know k is 2 successes, then you can plug everything into the binomial probability formula where it belongs. The other thing that's beneficial is that it's nice to say, okay, we can show this probability distribution where x is the number of successes. We can visualize what the 6 possible scenarios are. You could get anywhere from none of the 5 college students having energy drinks to all 5 of them having energy drinks. So this is the probability distribution. And what we just found right here, boom, let me get the pink one. What we just found here was the probability of getting 2 successes. So whatever this is the probability of getting 2 successes. Now we can go binomial PDF on that and do binomial PDF where we are going to type in n and p and the number of successes in order on a binomial PDF, and that is going to give us this probability right here. Now another reason why this is beneficial to picture this distribution like here, much like it was beneficial for us to say, hey, if we're doing a normal distribution, we're trying to find a probability, let's visualize, hey, we want to be above this value so we know that we're after that probability over there. Hey, this is a discrete probability distribution. That's continuous. So we got a similar thing here. All these probabilities add up to 1. So if we see a problem like, hey, what's the probability that you randomly select 5 people and at least one of them is an energy drinker, then you realize, oh, well, that's this probability right here that I could ever have anywhere from 1 through 5 energy drinkers. And knowing that all these probabilities here in the distribution add up to 1, we just go find this probability this probability right here. Now, taking that a step further, this one you don't need the binomial probability formula for, because there is only one way to end up with none of the 5 individuals being energy drinkers. That's for none of these, all 5 of these, to be failures. So how does that happen? Well, that would be a failure, which is 82% times a failure times a failure. That'd just be 0.82 to the 5th power. That would be your probability here. So the probability of at least 1 is 1 minus that probability right there. Now let's take this even a step further. If we're doing the binomial probability formula and we wanted to use that to find the probability of 0, then it brings up another important point, and that is this. You'd need the combination of 5 things, choose 5 things. Well, if you do the formula, then you're going to get 0 successes and 5 failures. You're going to get 0.18 to the 0 times 0.82 to the 5th, 0 successes and 5 failures. Now, we might say, wait a minute, we're going to be dividing by 0, and whenever you do that, that's undefined, so that's no good. But that is why, by definition, if you ever find yourself looking at a combination, at 0 factorial, 0 factorial by definition is 1. And so this is 5 factorial divided by 5 factorial, which is 1. And that again tells us, oh yeah, there's only one way to end up with no successes and 5 failures. So it just collapses down to this, which we determined earlier.